All right, let's talk about a really critical question in industrial safety. What happens when the flow just stops? It sounds simple, but one little mistake can lead to a huge disaster. But there's some pretty brilliant engineering design to prevent it. So let's get into it.
You know that classic riddle, right? Well, in an industrial plant, this isn't just some fun thought experiment. It's a very real problem engineers have to solve every single day. And in this case, the unstoppable force isn't a superhero. It's something way, way more common.
So before we get to things going wrong, let's just quickly look at what normal is supposed to look like. And it all starts with the heart of so many of these systems, the pump.
I mean, a pump's job is pretty straightforward. Keep the fluid moving through the pipes. It doesn't matter if it's oil or water or some complex chemical, the pump just provides that constant push to get it where it's got to go. It's a steady, reliable flow. This is the system working perfectly.
But what happens when that nice, smooth flow gets suddenly totally blocked? This is where our unstoppable force runs smack into its immovable object. You know, it often starts with a simple human error. Someone forgets a step or closes the wrong valve. But the pump, our unstoppable force, it has no idea. It just keeps on chugging along, doing its job, pushing fluid into a pipe that is now a dead end. And this right here is the core of the problem. The pump just keeps cramming more and more energy and pressure into a fixed space. That fluid isn't going to compress. The pipe is sealed tight, and, well, eventually, something has to give. This brings us to a really important term, deadhead pressure. This is the absolute maximum pressure that pump can generate when its outlet is blocked. It is the pump going all out, and that pressure builds up incredibly fast.
And when I say fast, I mean it. We're not talking about a slow buildup. The pressure can just skyrocket to hundreds of pounds per square inch in seconds. To put that in perspective, that's over 10 times the pressure you've got in your car's tires. And the result? Catastrophic failure. An explosion.
So, staring down that terrifying possibility, how do you prevent a disaster? Well, you engineer a last line of defense. You build in a critical layer of safety right into the system. The answer isn't to just cross your fingers and hope mistakes don't happen. Come on, we know they will. The real answer is to design the system with the assumption that things will go wrong, and then build in a safeguard that's ready to handle it. And that brings us to the hero of our story, the pressure safety valve, or PSV. This thing is an elegant, purely mechanical device that just sits on the pipe, constantly watching the pressure. There are no complex electronics, no computers. It just works on pure physics. The real beauty of the PSV is its simplicity. When the pressure hits a specific preset limit, the force is just strong enough to pop open a spring-loaded disc. Bam! An instant escape path is created. All that excess fluid gets vented to a safe place, like a flare system. Then, once the pressure drops back down, the spring just slams the valve shut again. It's simple, it's automatic, and it's a lifesaver. And this little device isn't just some add-on. It's a core part of a much bigger safety philosophy. Yeah, this kind of safety planning isn't just some random guesswork. It's all governed by these extremely detailed and rigorous engineering standards that spell out exactly how to prepare for almost any failure you can think of. Groups like the American Petroleum Institute, or API, they literally write the rulebook for this stuff. A standard like API 521 basically guides engineers on how to find every single potential cause of overpressure and then how to design a system to handle it. You pretty much have to be a professional pessimist for this job. And here is one of the most fundamental rules from that playbook. You have to design for one thing to go wrong. But you generally don't have to design for two unrelated things to go wrong at the exact same time. This core concept is called single jeopardy. This breaks it down perfectly. Single jeopardy is our blocked valve scenario. That's one credible failure, and the system absolutely must be designed to handle it. Now, double jeopardy would be that valve being closed at the exact same moment a completely unrelated power failure hits. This isn't about cutting corners. It's about practical, smart design. You focus your resources on preventing the most likely single failures, and that's how you build robust systems that are both safe and actually possible to build. And a blocked outlet is just one of those credible failures. The standards require engineers to think about a whole range of potential problems. Just look at this table. Besides our blocked discharge scenario, which, by the way, is often the most critical case because the PSV has to be big enough to handle the pump's entire flow, engineers have to plan for more. They calculate the pressure from an external fire, boiling the liquid in a tank,
They plan for control valves failing or a high-pressure tube bursting inside another piece of equipment. Each and every scenario needs its own specific, careful analysis to make sure the safety system can handle it. So the crucial point here is that this isn't about just one valve for one problem. It's a whole approach. It's about looking at a complex system, imagining all the ways it could realistically fail, and then building in layers of protection to make sure that no single failure leads to a catastrophe.
And that's really the key takeaway. The safest systems aren't the ones that never, ever fail. They're the ones designed to fail safely. From the circuit breaker in your house to the emergency brakes on a train, this principle is all around us. It kind of makes you wonder, doesn't it? What other invisible systems, designed by people planning for the worst, are keeping you safe right now?
When you think about massive industrial plants, there are a handful of worst-case scenarios that keep engineers up at night. And a massive fire is right at the top of that list. So today, we're going to pull back the curtain on the incredible engineering that's designed to stop a really bad day from becoming a total catastrophe.
So, picture this. You've got a gigantic pressure vessel, could be stories high, full of some kind of liquid, and all of a sudden, it's completely swallowed by an intense industrial fire. The real question is, what in the world is happening on the inside?
Well, the best way to describe what's happening inside that vessel is to call it what it is, a boiling cauldron. And believe me, the physics at play here are absolutely relentless.
Now, we're not talking about a little campfire here. The industry standard, API 521, defines the specific scenario. We're talking about an external fire, either a pool of burning liquid on the ground or a high-pressure jet fire that is just completely wrapping itself around this piece of equipment. So all that intense heat from the outside starts flooding into the vessel, and it begins to boil the liquid inside. And this isn't a gentle simmer, okay? It's a violent, raging boil that's creating a colossal amount of vapor. All that vapor has nowhere to go, so the pressure inside just starts climbing, and it climbs fast. You know, the easiest way to picture this is to think about a sealed pot of water you put on your stove, only you've cranked the burner up to the absolute maximum. We all know what happens next, right? If that pressure doesn't find a way out, that pot is going to fail, and it's going to fail violently.
So you're faced with this runaway train of pressure building up. How do engineers stop it? Well, they don't try to stop it. They give it an escape route, a very specific, very carefully engineered escape route.
And that brings us to the hero of our story, the pressure safety valve, or PSV for short. This thing is a purely mechanical work of art. It has no computers, no electricity. It's the last line of defense, and it's designed with one critical job in mind: to pop open all by itself when the pressure hits a dangerous level. In a fire, that PSV has a single vital mission. It's got to vent all that new vapor that the fire is creating. And here's the key: it has to vent it faster than the fire can make it. It's a race, really. If the valve can't keep up, the pressure will just keep on rising, and you're right back in the danger zone.
And that brings us to a really important number in the world of process safety. It might seem kind of random at first, but it is absolutely critical: 121%.
You see, according to all the engineering codes, even in a crazy emergency like a fire, the pressure inside a vessel is not allowed to go past 121% of its official design limit. That limit is called the Maximum Allowable Working Pressure, or MAWP. So the PSV's job is clear. It has to be big enough to dump all that vapor and keep the pressure below that absolute ceiling. No exceptions. Okay, so you need a valve that's big enough. But how big is big enough? Well, to figure that out, you have to size up your enemy. You have to somehow put a number on a force of nature like an industrial fire. Yeah, you can't just guess at this. The entire safety system hinges on one critical calculation. How much heat, exactly, is the fire pumping into that liquid? That number is going to determine everything that comes next.
So engineers have these detailed formulas, and they plug in a few key factors. They look at how intense the fire is, whether there's any fireproof insulation on the vessel, and maybe most importantly, something called the wetted surface area. That's just the part of the vessel's metal skin that's actually touching the boiling liquid on the inside. And this is where it gets really cool. This quote from API 521 points to a piece of hard-won wisdom. It basically says that even if a vessel is, say, 100 feet tall, years of real-world data have shown you only need to worry about the heat coming in on the bottom 25 feet.
It's this fascinating practical rule of thumb that makes a crazy hard calculation actually manageable. All right, so once you know exactly how much heat is getting in, you can finally start designing that escape route. You can translate that calculation into actual physical hardware. And the logic here flows perfectly. First, you calculate the total heat getting absorbed using all those factors we just talked about. Second, you take that heat number and figure out exactly how many pounds or kilograms of vapor are being created every single hour. And then finally, you go pick a safety valve that is specifically designed to handle that exact flow rate. And this just shows you the kind of detail we're talking about. To get from heat in to vapor out, engineers need a special property of the fluid called its latent heat of vaporization. That's just a fancy way of saying how much energy does it take to turn this stuff from a liquid into a gas. And they use these incredibly detailed charts to find that exact value for the extreme conditions happening during a fire. But here's the thing, relying on a single device, no matter how tough it is never a good idea. True safety, real industrial safety, always comes from having multiple layers of defense.
It is so important to remember that the PSV is designed to be the absolute last resort. The real goal is to never need it in the first place. Good process safety is like an onion. It's got a lot of different, independent layers of protection. And here are just some of those other layers. You could have water spray systems, basically giant sprinklers to cool the vessel. Special fire-resistant insulation can buy you precious time. There are even automated systems that can rapidly vent the vessel to a flare stack. Even simple things like building walls to contain a spill or burying a tank in the earth can make a huge difference.
So, if there's one thing to take away from all this, it's this. Safety isn't about finding one magic bullet. It's about building a robust system where multiple, independent safeguards are all working together so that even if one layer fails or even two, the plant, and more importantly, the people, stay safe. Now, we've gone deep on what happens in an external fire, but that's just one of dozens of potential ways a vessel can be overpressured. Engineers have to plan for all sorts of other what-ifs, like a blocked pipe, a chemical reaction that goes haywire, or an internal pipe bursting. Each and every one of those scenarios needs its own unique analysis and its own layers of protection.
All right, today we're going to dig into a safety issue that's super important but also really easy to overlook. What actually happens when you trap liquid inside a pipe and it starts to heat up? The answer is surprisingly powerful, and we're going to use the industry go-to guide, API 521, to figure it all out. So, let's just start with a simple thought experiment. Picture this. You've got a pipe full of some cold liquid. You shut the valves on both ends so it's totally trapped. Then you just leave it out in the sun. What do you think happens? I mean, it sounds pretty harmless, right? Well, the physics of thermal expansion can turn that simple setup into a recipe for disaster.
To really get a grip on this, we need to break down what engineers call the trapped liquid problem. It's not complicated, really. It just comes down to 3 key ingredients coming together at the same time.
Okay, first up, you need a pipe or a tank that is completely 100% full of liquid. And that's the key phrase here, liquid full. There's no air gap, no vapor cushion at the top, nothing. It's just wall-to-wall liquid. Second, that line full of liquid gets totally cut off from everything else. You close a valve on one side, you close another valve on the other side. Now that liquid is officially blocked in. It has absolutely nowhere to go. It's stuck. And for our third and final ingredient, you just need to add a little bit of heat. Now, we're not talking about a massive furnace here. Like API 521 points out, the most common culprits are things you see every day, like the sun just beating down on a pipe, or maybe some heat tracing that's used to keep pipes from freezing in the winter. That's it. So you take those 3 things, a full pipe, blocked-in ends, and a heat source, and what do you get? You get what the standards officially call hydraulic expansion. It's just a fancy term for a simple fact. When you heat a liquid up, it wants to take up more space. And this is the absolute core of the whole issue. Okay, so the stage is set. We've got our trapped liquid. It's getting warmer. Now what? Let's look at the consequences, because this is where a simple situation starts to get pretty serious pretty fast. Here is the absolute crux of the problem. Unlike a gas, which you can squish and compress, liquids are, for all practical purposes, incompressible. You just can't squeeze them into a smaller space. So when that trapped liquid heats up and tries to expand, it has no choice but to push, and it pushes hard on the walls of the pipe. And here's the real kicker. Since that liquid can't be compressed, and it can't escape, all that energy from its expansion gets converted directly into pressure. And we are not talking about a slow, gentle rise here. The pressure can absolutely skyrocket with just a few degrees of temperature change. It can easily blow past the pipe's design limits and create a very real risk of a rupture.
But you might be wondering, okay, how much does it actually expand? And that's a fantastic question, because it really depends on what the liquid is. And the differences can be huge. This is a detail that is absolutely mission critical for the engineers designing these systems.
Take a look at this table. It's based on data right out of API 521. Now, don't get too hung up on the term cubic expansion coefficient. Just think of it as a get bigger number. The higher the number, the more that liquid expands when you heat it. So just look at the number for water, and now look at the one for a light hydrocarbon. It's way, way bigger.
And if that table didn't quite paint the picture, this chart definitely will. I mean, look at that difference. It's massive. For the exact same temperature increase, a light hydrocarbon like gasoline expands about 7 times more than water does. So yeah, a pipeline full of gasoline sitting in the sun is a whole different and much more dangerous ballgame. So we've got this massive, hidden force just building up inside a pipe, waiting to pop. How in the world do you solve for that? Well, thankfully, the solution is actually incredibly simple and kind of brilliant. Let me introduce you to the hero of our story, the thermal relief valve, or TRV for short. This little guy is a specialized pressure relief valve with one job and one job only, to protect pipes and vessels from hydraulic expansion. They're usually tiny because they only need to let out a teensy bit of liquid. So here's how it plays out. As the liquid expands, the pressure in the pipe climbs. Once it hits the TRV's set pressure, that magic number, the valve just cracks open a little bit. It's not some big violent whoosh. It's more of a tiny weep. Just a few drops of liquid sneak out. And that's it. That tiny release is enough to instantly drop the pressure back down to a safe level. Problem solved.
So, we've talked about a trapped liquid, the sun, and a tiny valve. Why is this seemingly small detail so important? Let's just pull back for a second and recap the crucial safety lessons here.
The big takeaway here is that a blocked-in line full of liquid is a serious hidden hazard. Even something as simple as the sun can generate enormous, dangerous pressures. We've seen that what's in the pipe matters a lot. And most importantly, sometimes a tiny, inexpensive valve is the only thing standing between a normal day and a catastrophic failure. It's a perfect example of why the small details in engineering design are absolutely everything when it comes to safety. It kind of makes you think, doesn't it? What other invisible forces, what other little bits of hidden physics are out there creating these everyday engineering challenges? It just goes to show you, understanding these fundamental principles is what keeps our world running safely. Thanks for digging into this with me.
Behind our modern world, there are these massive industrial plants just humming along, powering our lives. But they operate under incredible pressure, and keeping them safe is, well, it's a huge deal. Today, we're going to zero in on one single critical point of failure, the control valve, and the really brilliant engineering that's designed to stop a disaster before it starts. So let's dive in and see how engineers tackle this.
I mean, it's a pretty direct question, right? But it's one that engineers have to answer, seriously, every single day. You've got these vessels holding fluids at pressures that are just mind-boggling. So what happens when something goes wrong? How do you actually prevent the worst from happening? Well, the answer isn't just about building stronger pipes. It's really a whole philosophy. You start by assuming that things will fail. And then you design your systems to handle that failure in the absolute most extreme, worst-case scenario you can possibly imagine. To really get the solution, first we have to appreciate the scale of the problem, and right at the heart of all of it is one thing, just immense, constant pressure. Think about an oil refinery or a chemical plant. It's basically a massive, complex network of arteries, and inside all those pipes and vessels, you've got fluids kept under enormous pressure. That's what makes them react or separate or just flow. Keeping that pressure inside safe limits is the whole game. Okay, so that pressure is managed by all sorts of automated systems. But what happens when one of those automated gatekeepers just breaks? And that brings us right to the core of what we're talking about today, the failure of a control valve. So what exactly is a control valve? Honestly, the easiest way to think about it is as the system's automated hand on a faucet. It's always making tiny adjustments, opening a little, closing a little, to perfectly regulate the flow and pressure. It's getting commands from a central brain, and it's an absolutely crucial piece of the puzzle. Now here's where it gets interesting.
A control valve can fail in two main ways. On one side, you've got fail open. This is like your faucet breaking and getting stuck completely wide open. High-pressure stuff just floods into a vessel way faster than it can get out. Then on the other side, you've got fail closed. This is the exact opposite problem. The exit door slams shut and gets stuck. Flow just stops cold, and the pressure starts building up behind it like a dam about to burst. Either way, you're looking at the same scary outcome, a super fast, uncontrolled pressure spike.
So, with those two nightmare scenarios, how do you even begin to design a safety system? You might think you try to plan for everything going wrong at once, but engineers actually follow a very specific and kind of counterintuitive rule.
And this right here is a huge deal. It's straight from API Standard 521, which is pretty much the Bible for this stuff. It says you do not design for two unrelated things going wrong at the exact same time. You don't assume a control valve fails and a fire starts at the same moment. Now, that might sound a little risky, but trust me, there's a really good reason for it. And this is the reason why. It's a concept called single jeopardy. The whole idea is to focus on one single believable failure, like our control valve failing open, and then you assume it happens in the absolute worst, most catastrophic way it possibly can. See, if you design a safety system that's tough enough to handle that one epic failure, you've built something that is both practical to engineer and incredibly effective. So that's the philosophy, but how does it turn into a real piece of hardware? If you've designed for that single worst-case scenario, what's the actual device that comes in and saves the day?
First, a little bit of context. As you can see here, a control failure is just one of many ways pressure can get out of hand. Engineers have to plan for everything from blocked outlets to fires. Our focus is that one in bold, but every single one of these possibilities needs a bulletproof last line of defense.
And here it is, the pressure relief device, or PRD. This is the ultimate mechanical safety net. It's not smart, it's just brutally simple and reliable. As the pressure builds up, it physically shoves this valve open at a very specific point. The valve just snaps open, and all that dangerous excess pressure gets vented away to a safe place, like a flare stack. It's the system's big red emergency eject button.
All right, so we've got the problem, we've got the philosophy, and we've got the solution. But how do we make sure that everyone, everywhere, builds these systems to the exact same life-saving standard?
Well, that's where documents like API 521 come in. This thing isn't just a manual, it's the collected wisdom of an entire industry, all written down. It creates a universal language and a strict set of rules, making sure a plant in one part of the world is designed with the same safety DNA as one on the other side of the planet. It's basically decades of lessons, a lot of them learned the hard way, all there to protect people and the environment. And really, that's the key takeaway here. Industrial safety is a whole system. It starts by pinpointing a risk, like our failing control valve. Then you apply a clear philosophy, like single jeopardy, and you use standardized, proven engineering to build the safeguard. That's how an abstract danger becomes a concrete, life-saving reality. And that kind of leaves us with one final thought to chew on. As our technology gets better and our industrial processes get even more complicated and automated, the ways things can fail will also change. You have to wonder, what new worst-case scenarios will the next generation of engineers have to plan for? Thanks for tuning in.
You know, deep inside pretty much any industrial plant, we're talking refineries, chemical facilities, you name it, there are these silent workhorses chugging along 24/7. They're called heat exchangers. And their job sounds simple, right? Just transfer heat between two fluids without letting them mix. But what's really going on inside those steel shells is this incredible amount of contained energy, a constant battle between high and low pressure. And for years, they just do their job perfectly. No drama. But what happens when one of those workhorses fails? And not over time, but in a fraction of a second. Well, that's what we're going to unpack today. The anatomy of a truly powerful and violent event, a heat exchanger tube rupture. So to really get what goes wrong, we first got to understand how they work when everything's going right. We're going to focus on a super common type, the shell and tube heat exchanger. And really, it's all a tale of two different worlds, two completely separate pressure zones living side by side.
Okay, so the key thing to wrap your head around here is the pressure difference. On one side, you've got the tube side. Picture a high-pressure fluid, maybe some hot oil, just cruising through a whole bundle of tubes. Then, all around those tubes, you have the shell side, and that's filled with a much lower pressure fluid, like cooling water. As long as those tubes stay in one piece, everything's great. Heat moves, the process works, no problem.
But see, in one piece isn't a guarantee forever. With all that pressure, temperature, and vibration, a tube can fail. And I'm not talking about a tiny little pinhole leak. Oh no, we're talking about something way more sudden, way more catastrophic. So, the industry has a term for this absolute worst-case scenario. It's in the API 521 standard. That's kind of the rule book from the American Petroleum Institute for this stuff, and they call it a full-bore tube rupture. But a much better name for it? A guillotine break. Just think about that. The tube doesn't crack or leak. It snaps, clean in two, instantly, like it was just sliced. And in that instant, the moment that tube snaps, the wall between high and low pressure just vanishes. The high-pressure stuff from inside the tube erupts into the low-pressure shell. And because we're dealing with liquids here, this doesn't just create a leak, it creates a shockwave.
And this is where it gets really crazy. The immediate danger isn't just about, mixing two fluids that shouldn't be mixed. It's about the brutal physics that this event unleashes inside a sealed steel container. This is so much more than a simple leak.
One of the most powerful things that happens here is something called flashing. So you've got this high-pressure liquid, right? When it blasts into the low-pressure shell, that pressure drops like a rock. And what does the liquid do? It boils, instantly. It violently expands into a huge volume of vapor. A tiny bit of liquid becomes a massive cloud of gas in a microsecond. So this creates a total double whammy for the safety system that's supposed to protect the shell. First, it's got to handle that initial hydraulic shockwave, the raw blast of liquid. And then, at the exact same time, it has to deal with the gigantic, expanding cloud of vapor from the flashing. It's a 1-2 punch that can completely overwhelm a system that's not ready for it. So how on earth do engineers prevent a catastrophic failure? Well, they don't guess. They follow a very strict set of rules. The engineering Bible for this whole scenario is API 521, and it mandates exactly how you have to design for the absolute worst. API 521 basically lays out a non-negotiable checklist. Step 1. You have to assume the worst case, that full guillotine break of one tube. No hoping for a smaller leak. Step 2. You have to calculate the total flow gushing out of both broken ends of that snapped tube. And step 3, and this is so important, you must account for all that extra volume created by any liquid that flashes into vapor. There's just no room for optimism. You plan for the absolute biggest disaster you can imagine.
Okay, so even if you have a relief device that's big enough to handle this massive flow, there are two other things that can mean the difference between a contained event and a ruptured vessel: speed and location. And trust me, they are completely connected.
And you don't have to take my word for it. The standard itself explains this perfectly. I'm reading right from it. The time interval in which the shockwave is transmitted to the relieving device increases if the device is located remotely. So what does that mean in plain English? It means if your safety valve is way down the pipe, that shockwave could literally tear the exchanger apart before the pressure wave even gets to the valve to open it. The response has to be instantaneous. So let's boil it all down. What are the key takeaways for building a system that can actually survive this? First, you need incredibly fast-acting relief devices, like rupture discs, that open in milliseconds. A normal valve is just too slow. Second, you have to bolt that device directly onto the equipment, or as close as you can possibly get it. No long stretches of pipe. And finally, you have to always respect the power of that initial shockwave. It's a race against physics, and you just can't give the shockwave a head start.
You know, this whole thing really comes down to a fundamental question at the heart of all industrial safety. When we're designing these systems, are we planning for what's just likely to happen? Or are we planning for what would be truly devastating if it ever did? When it comes to a tube rupture, the rules make the answer crystal clear. You plan for the shockwave.
Today, we're pulling back the curtain on the invisible world of industrial safety. We're going to look at the incredible automated systems that are often the only thing standing between a normal Tuesday and a full-blown catastrophe. Let's get into it. And it's a great question, right? Because when you have these huge, complex facilities churning with energy and often volatile materials, the biggest threat, well, it usually comes from the inside, from the failure of the very systems that are supposed to keep it all running smoothly. So to really get a grip on the risk, you first have to think of a plant as, well, almost like a living thing. It has critical support systems, just like we do. This is such a great way to think about it. The electrical power, that's the heart, pumping energy through the whole facility, driving all the critical equipment. The cooling water is the circulatory system, the plant's blood, carrying away all that intense process heat. And the instrument air,
That's the nervous system, sending tiny pulses of air to control thousands of automated valves, the muscles of the plant. Yeah, each one is absolutely vital. If even one of them goes down, you don't just have a small problem. You have the first domino in a potentially catastrophic chain reaction. So, what happens when the plant's heart just stops beating? So, let's play this out. Let's look at one of the biggest scenarios engineers have to plan for: a total site-wide power failure, a complete and sudden blackout. The second the power is cut, a very dangerous chain reaction kicks off. The heart stops. And that means all the pumps moving cooling water and all the fans on the air coolers, they just shut down. The circulatory system grinds to a halt. And with no way to get rid of the incredible amount of heat being generated, the temperature inside all that equipment starts to climb really, really fast. As that temperature rises, the fluids inside start to boil and expand, creating more and more vapor. And here's the critical part. That vapor is trapped. It has nowhere to go. So the pressure just builds and builds at an absolutely alarming rate, threatening to literally tear steel pipes and vessels apart from the inside. And this right here, this brings us to the big bad of our story. The fundamental danger that all these safety systems are built to fight: overpressure.
Simply put, overpressure is when a system is being pushed way beyond its breaking point. It's like overinflating a tire. But we're talking about a situation where the pop could flatten a building. And under just the right, or I guess wrong conditions, this can escalate into something much, much more violent.
And this is where things get genuinely terrifying. If a pocket of cooler liquid, say water from a leak, suddenly hits a superheated metal surface, it doesn't just boil, it flashes to vapor. Instantly, we're talking microseconds. The source calls this a rapid phase transition, but you can think of it as a physical explosion. The instantaneous expansion creates a shock wave that's just like a detonation.
And this quote from the industry standard API 521 is honestly pretty chilling. What it's saying is that against this kind of event, even the main safety devices are completely useless. It's not a leak you can vent, it's a shock wave. This is exactly why preventing that overpressure from ever reaching this point is so incredibly important.
So, if you can't contain that runaway pressure, what do you do? Well, you have to give it a safe way out. And that brings us to the engineering solution: the escape route. So meet the unsung hero of industrial safety, the pressure relief valve, or PRV. This thing is a marvel of engineering. It's totally mechanical, basically a super-calibrated, spring-loaded guardian. It doesn't need power or computers or any person to flip a switch. When the pressure inside hits a specific preset limit, that force physically shoves the valve open. It's beautifully simple, and because of that, it's incredibly reliable. Okay, so what happens when that valve pops open? Well, all that high-pressure gas doesn't just shoot out into the open air. No way. It's immediately channeled into a special network of pipes called a flare header. You can think of this header as a highway system, collecting all the relieved gases from all over the plant and routing them to one single, safe place for disposal: the flare. The flare you see burning at a plant isn't a sign that something is wrong or wasteful. It's a sign that the safety system is working exactly as it should. It's like a giant safety candle, burning off potentially flammable or toxic gases and converting them into much less harmful things before they ever reach the atmosphere or the community. Now, this whole network, the valves, the pipes, the flare, it wasn't just invented on the fly. It's the result of decades of real-world experience and super rigorous engineering. And it's all written down in a global rulebook. And that rulebook is API 521, which is the source for this whole explainer. It's the standard that engineers all over the world use to make sure these life-saving systems are designed the right way. It tells them exactly which scenarios they have to plan for, how to calculate the mind-boggling amount of gas that can be released in an emergency, and how to build a system that is guaranteed to work when everything else has failed. A really core idea from API 521 is something called single jeopardy. Here's how to think about it. Your car has airbags to protect you in a crash. That's a single failure, the crash. But engineers don't design the car assuming the airbags will fail at the exact same time that, a tree falls on the engine for a totally separate reason. That's double jeopardy. Two unrelated failures happening at once. Safety systems are designed to handle any single credible failure, like losing power or losing cooling water, because trying to plan for every wild combination of disasters would be literally impossible.
And this planning, it is not guesswork. It is hardcore science. I mean, look at this chart. It's taken right from the standard. It might look like a crazy web of lines, but it's an incredibly precise tool. It lets an engineer plug in a specific chemical at a specific pressure and temperature and calculate exactly how much vapor is going to be generated during that power failure scenario we talked about. Every single one of those relief valves is sized with this level of scientific detail. This is what keeps these massive facilities from turning into bombs.
So here's the big takeaway. Every single piece of equipment in a plant is protected by a system that is designed to handle its single worst credible day. When you see a flare, you're not seeing a problem. You're seeing one of those systems doing its job perfectly. And it really makes you wonder, just how many of these silent, invisible guardians are out there, all around us, keeping things safe every single day?
All right, let's dive into a really critical safety scenario, one that comes straight from the engineering rulebook, API 521. We're going to explore what happens when layers of protection fail in a very specific and, you'll find, a surprisingly predictable way. It's the kind of question that keeps engineers up at night, right? Today, we're looking at a situation where a simple system gets pushed to its absolute limit by what, on the surface, just looks like incredibly bad luck. But as we're about to see, it's not really about luck at all.
Okay, so to really get to the heart of the problem we're about to unpack, we first need to look at a fundamental and, honestly, an often overlooked component in almost any industrial piping system.
A check valve is, well, it's basically a bouncer for a pipe. It's a simple mechanical device with just one job. Make sure that fluid flows in one direction and only one direction. But, like any mechanical part, it's not perfect. Over time, it can wear down, stuff can get stuck in it, and it can fail silently, stuck in the open position.
So, keeping that one-way street in mind, let's set the stage for a crisis. This is a scenario that engineers are absolutely required to anticipate, precisely because the consequences can be so severe. And bam, the first domino falls. You've got this high-pressure pump, it's the heart of the operation, and it suddenly trips, it just stops working. Could be a power failure, could be a mechanical issue, doesn't matter. The forward flow, it's now zero. And this is where things get dangerous. That one-way door we were just talking about, it fails. Or more accurately, we discover that it has already failed. And now, all that high-pressure fluid downstream has a wide-open invitation to come rushing backward right into the low-pressure system it just came from. The results are immediate and they can be absolutely catastrophic. Low-pressure equipment like the vessel feeding the pump is just not designed for this kind of sudden pressure surge. The pump itself can be spun backward and completely destroyed. But the worst-case scenario? A loss of containment. We're talking a rupture, a leak, which is a major safety and environmental disaster.
So this is the natural question, isn't it? A pump fails and a valve fails at the exact same time. That sounds like two totally separate, unrelated things going wrong at once. I mean, surely you can't be expected to plan for that kind of misfortune. Or can you?
Well, this is where it gets really interesting, because engineering safety standards see this very differently. It's not considered bad luck at all. Instead, it gets classified as a single credible failure. And it all comes down to a concept called the single jeopardy rule. This lays out the key distinction perfectly. You see, engineering safety has this idea of double jeopardy. That's two unrelated things happening at once. You don't typically have to design for that. But then there's single jeopardy, which is one credible thing going wrong, and you absolutely must design for it. So which category does our scenario fall into? And here is the big twist. This is where our whole understanding of the event has to shift. What if the check valve failure wasn't a new event at all? What if it had already failed, days, weeks, or even months ago, and was just sitting there, broken, waiting for the right conditions to reveal itself?
This is what's known as a latent failure. Think of it like a crack in a dam that's totally invisible until the water level rises. The fault is already there, just dormant. The pump trim doesn't cause the valve to fail, it simply exposes the pre-existing failure.
And you don't have to take my word for it. This standard itself makes this crystal clear. API 521 explicitly says this is not double jeopardy. The pump trip is the initiating event, sure, but the check valve's latent failure is a pre-existing condition. Therefore, the combination is considered a single credible scenario that the system's design must be able to handle safely. So if you have to plan for it, how exactly do you do that? Let's move to the solution and see how this all builds into a safer system design, turning a potential catastrophe into a totally managed event. The engineering process is really methodical. You start by assuming the check valve has already failed. That's your starting point. Then you calculate the absolute worst-case reverse flow that could happen when the pump trips. Finally, and this is the critical step, you make sure that the pressure safety valve on the low-pressure side is big enough to handle and safely vent that entire reverse flow, protecting the equipment from getting blown apart. Now, handling the failure is good, but preventing it is always better. So what if you could stop that dangerous reverse flow before it ever really begins? According to the very same API standard, the most robust form of prevention often comes down to this simple, elegant number, 2. And here's the logic. The standard points out that if you install 2 check valves, one right after the other, you get some powerful redundancy. The probability of one valve having a latent failure is something you have to plan for. But the probability of both having a latent failure at the same time, well, that becomes incredibly small. This approach gives you a really robust layered defense. One valve can be broken, totally hidden from view, but the second one is still there to do the job. But, and this is a huge but, there's a critical catch. This only works if the devices are regularly inspected and maintained. Without that, you're just doubling your chances for a hidden failure. So let's bring it all together. What looks like a freak accident, a pump and a valve failing at once, is actually a single predictable risk when you account for these hidden latent failures. And this completely reframes the whole perspective, from reacting to accidents to proactively designing systems that are resilient enough to handle them. And this leaves us with the fascinating question to chew on. This principle of latent failure applies far beyond just industrial plants. Think about the systems in your car, your home, or even in finance. What other scenarios that we dismiss as just bad luck are actually single manageable risks, just waiting for the right trigger to be revealed? You know, in the heart of any of those huge industrial plants you see, there's this hidden world of pipes and vessels and valves. It's kind of like a giant circulatory system, working silently 24/7, making all the stuff we use every day. And inside that system, there are these invisible guardians, designed for moments that, well, you hope never ever happen. Today, we're going to pull back the curtain on one of these unsung heroes and see how it stops a total catastrophe in its tracks. So let's start with a pretty chilling question, right? In this world of super complex procedures and automated everything, could something as simple as one person turning the wrong handle unleash chaos? Could one wrong turn really lead to disaster? Well, the answer is kind of surprising. Okay. To really get what happens, we first have to understand the environment we're in. We're basically going inside a massive high-stakes plumbing system. I want you to imagine 2 completely different worlds existing right next to each other. In one, you've got stuff under enormous pressure, just rocketing through the main arteries of the plant. And in the other world, you have these big vessels that are operating at much, much lower, gentler pressures, for processing or just for storage. The energy difference between these two is just massive. Think about that high-pressure header on the left. It's like a tightly coiled spring, holding a ridiculous amount of force in check. But the low-pressure vessel on the right, it's just not built for that. It wasn't designed to handle anywhere near that kind of raw power. And here's the kicker. Connecting these 2 completely different worlds is often something as simple as a bypass valve. Just a hand wheel on a pipe. That's it. It's the one gatekeeper standing between calm and total chaos. All right, now let's see what happens when that gatekeeper is opened at the wrong time. This is where our story goes from just another Tuesday to a critical event that's going to unfold in a matter of seconds. Now, this isn't some act of sabotage or anything like that. It's not negligence. It's a simple, honest-to-goodness human mistake. The kind of thing that can happen to anyone in a complex job. But the consequences of turning this one wheel, they are instantaneous and they are huge. The gate is now wide open. This is the absolute best way to picture what's happening. It is literally like connecting a high-pressure fire hose to a party balloon. All of that stored-up energy from the high-pressure side is now just screaming, totally unimpeded, into a vessel that has no possible way to contain it. So let's watch the numbers. The vessel is normally sitting pretty at around 50 pounds per square inch, or PSI. Everything's stable, but not for much longer. In just a couple of seconds, the pressure has tripled. The steel walls of that vessel are already groaning, right? They are being stressed way beyond what they were ever meant to handle.
And now we're at 300 psi, and it's still climbing. Alarms are absolutely blaring. We are deep in the red zone now. The vessel itself is probably starting to bulge, its very structure being pushed to the breaking point. And the only thing that matters now is this red line, MAWP. It stands for Maximum Allowable Working Pressure. And that's not a guideline. It's the engineered point of catastrophic failure. We are seconds, literally seconds away from a rupture. Seconds from disaster.
But right here at the climax, our story introduces its hero. And it's not a person. It's a purely mechanical device that's been sitting there silently, just waiting for this exact moment its entire life. So say hello to the pressure safety valve, or PSV. Its job is incredibly simple. When the pressure gets too high, it opens. That's it. It's the absolute last line of defense, a mechanical fail-safe. You know, the absolute beauty of the PSV is its simplicity. There's no computer, there's no electricity, no person has to push a button. It's just pure physics. As the pressure builds up, it pushes against a little disc that's being held down by a very carefully calibrated spring. And when the pressure pushing up is finally stronger than the spring pushing down, pop! It slams fully open, instantly creating a massive escape path for that pressure. And just as our vessel is on the absolute brink of failing, the PSV goes off. With this incredible roar, it vents all that dangerous overpressure, directing that energy away from the vessel and into a special disposal system. It saves the equipment, and way more importantly, it saves the people working nearby. Now, you might be sitting there thinking, wow, that was a really close call, a lucky break. But here's the thing, it wasn't. What we just saw was not a near miss, it was the system working exactly, perfectly, as it was designed to. Let's talk about the foresight that goes into this. So where does all that vented gas go? Well, it doesn't just disappear into the air. It gets funneled into this really sophisticated safety net. First, it goes into a big pipe called a flare header. Then, any liquids get dropped out in what's called a knockout drum. And finally, the leftover gas is sent up to a flare tip where it's burned off safely and completely. The whole thing is a system designed to handle the absolute worst-case scenario. So this is the really critical takeaway. We have to reframe how we see an event like this. Yeah, the human error was the cause, but the successful pop of that PSV and the flare system lighting up, that was the intended effect. You're looking at a real-world, full-scale test of a safety system, and it passed with flying colors.
This whole way of thinking is actually written down in industry standards, like API 521. This quote here explains a core rule called single jeopardy. Basically, it means engineers don't have to design for two completely unrelated things going wrong at the exact same time, like, say, a valve failing open and an external fire starting at the same moment. Instead, they focus like a laser on all the credible, single things that could go wrong.
And that brings us to what I think is the most fascinating part of all. The entire scenario we just walked through, that operator mistakenly opening a valve, it wasn't some random, unpredictable event. It's actually a classic case study pulled straight out of the engineering safety playbook. Just look at this table. It's based right on that API 521 standard, and it lists out all the known ways a vessel can get overpressured that engineers have to design for. And would you look at that? Right there, highlighted, reference 4.4.92, inadvertent valve opening. Our exact scenario. It's not just something they think about, it's a mandatory design case they have to solve for. And that just brilliantly shows you the incredible depth of process safety engineering. They do this for everything. Engineers look at every single piece of equipment and they ask, what if? Over and over and over again. They figure out all the credible ways it could fail, and then they build in robust safety systems, like our PSV, to protect against it. So the next time you're driving by a plant and you see a flare light up the night sky, you'll know that it's probably not a sign that something has gone wrong. More often than not, it's a sign that a safety system has just worked perfectly. It really makes you wonder, doesn't it? What other invisible guardians like this are engineered into the world all around us, just silently keeping us safe every single day?
You know, inside those massive industrial chemical plants, there are these vessels just humming with incredible controlled power. We're talking about the reactions that create, well, everything from the plastics in our lives to life-saving pharmaceuticals. But what happens when that control is just gone?
It's a question that probably keeps a lot of chemical engineers up at night. I mean, think about it. What could possibly be more dangerous than a really powerful chemical reaction?
The answer? One you can't stop. That's what we're talking about today, a runaway reaction. It's a truly catastrophic event that, unfortunately, has been at the heart of some of the worst industrial disasters in history.
To really get why these things can become so unstoppable, we kind of have to shrink down and go right inside the reactor itself. And what you'd find is a process that's always generating its own energy, its own heat. It's a process that we call exothermic.
So at its heart, an exothermic reaction is pretty simple. It makes its own heat. Think of a type of hand warmer you shake to activate. Now imagine that exact same idea, but instead of just warming your hands, it's powerful enough to create the materials for your phone or the medicine you might take. That's the kind of scale we're dealing with here.
So inside a reactor, all that heat has to be constantly pulled away by a cooling system. It's this really delicate balancing act, right? Heat's being generated and heat's being removed. And as long as that balance is perfect, everything's stable, everything's safe.
But, every finely tuned balance has a breaking point. And when this one breaks, it's not just some small failure, it's a full-blown crisis. This is the moment the reaction starts to, run away from us.
And it can be triggered by just a few really critical failures. You could have a total catastrophic breakdown of the cooling system, or maybe the agitator, the thing that's supposed to be stirring and keeping everything mixed, it just seizes up. Or, and this is a big one, a catalyst. The very thing that's supposed to control the reaction speed gets added wrong. Any one of those can light the fuse.
And this is where the chain reaction just takes off. The cooling fails, so the temperature starts climbing. But wait, higher temperatures make the reaction go even faster. A faster reaction, that generates even more heat. You see the loop here? It's this vicious self-feeding cycle, causing the pressure inside that sealed vessel to just skyrocket. The reactor has literally become a ticking time bomb. So, with pressure building like crazy and a disaster on the verge of happening, how do you stop it? You can't just flip a switch. Engineers have to rely on one last line of defense, a device designed for exactly these kinds of catastrophic overpressure events. It's called a pressure relief device, or a PRD. Honestly, the easiest way to think about it is like that little pop-off valve on a pressure cooker. When the pressure just gets too high, pop! It opens up to vent the excess and hopefully bring everything back to a safe level.
Seems pretty simple, doesn't it? The pressure gets too high, a valve opens up, problem solved, right? But what if it's just not that simple?
Yeah, it's almost never that simple. The very physics of the runaway reaction itself creates this absolutely massive engineering challenge. That simple little valve has to somehow account for an incredibly complex, chaotic, and violent event.
And the heart of that challenge comes down to this really fundamental difference in the physics of the reaction. It's a concept so critical, it's actually written into the rule books for preventing industrial disasters, these engineering standards like API 521.
Okay, so engineers split these runaways into two basic types. On one hand, you've got a tempered system. Here the reaction is producing something that can be condensed, like steam. The cool thing is, the act of boiling itself uses up a ton of energy, which acts like a natural brake on the temperature. But then, you have a gassy system. This one produces non-condensable gases. There's no boiling to slow things down. It's like flooring the accelerator on a car that doesn't just have no brakes, it's actively building a bigger, more powerful engine as it speeds up. And that is the terrifying reality of it. For one of these gassy runaways, that little safety valve has to be big enough to vent a totally enormous, superheated volume of stuff, and it has to do it fast enough to literally outrun the reaction's own exponential heat generation. It's a monumental challenge.
So, faced with this, let's be honest, this seemingly impossible physics problem, how do engineers actually solve it? I mean, how do you design for a disaster that you hope never ever happens? Well, they turn to a seriously advanced toolkit.
To get the size of that safety valve right, engineers can't just take a guess. They have to, in essence, predict the future of a completely chaotic event that unfolds in just a fraction of a second. To do that, they use something called dynamic simulation. You can think of it like a super accurate weather forecast, but for a chemical disaster happening inside a steel box. These computer models let engineers simulate the entire runaway scenario from the first trigger to the final outcome, predicting the exact pressures and flows they'll have to deal with. And this isn't just some theoretical idea, it's hardcore proven science. The industry knew this was a huge safety gap. So they created the Design Institute for Emergency Relief Systems, or DIERS. As the official standard, API 521 puts it, DIRS ran this intensive research program to figure out exactly how to design these emergency systems. That research became the absolute gold standard for taming these dangerous reactions. So this DISRS methodology, it's the playbook. It gives engineers that rigorous, research-backed framework they need. It's what lets them confidently size that last line of defense, making sure it's actually strong enough to work when everything is on the line.
All right, so let's zoom out a bit from all the schematics and the physics. Why does all of this incredibly specialized, super complex work actually matter to, well, all of us?
Let's just boil it all down to the key takeaways. First, runaway reactions are a massive exponential threat. Second, that simple-looking safety valve is anything but a simple solution, all thanks to some really complex physics. Third, to get it right, advanced tools like dynamic simulation and that DIRS methodology are absolutely critical. And finally, all of this life-saving knowledge gets codified in engineering standards like API 521, so everyone can use it.
This whole process, this is the unseen shield. It's the invisible, brilliant engineering that prevents disasters, and it safely turns all of that immense chemical power into the products that we all use and rely on every single day. And that really leaves us with one final thought, doesn't it? What other invisible systems of control, of prevention, are quietly working all around us, keeping our world safe, right this very second?
You know, in industrial engineering, we spend a ton of time thinking about how to contain enormous pressure. But what if the biggest danger isn't from what's trying to get out, but from the invisible force of the air trying to get in? Let's dive into the wild physics of a catastrophic implosion. So, when you think about a huge industrial tank failing, what's the first image that pops into your head? Seriously, picture it for a second. It's probably something pretty dramatic, right?
Exactly. You're probably thinking of a massive, high-pressure rupture, a crazy, outward explosion that sends metal flying everywhere. And look, that is absolutely a real and critical failure that engineers have to design for day in and day out.
But there's this other type of failure. It's just as destructive, but it's totally counterintuitive, an implosion. A sudden catastrophic inward collapse. And this isn't caused by pressure on the inside, but by the crushing force of the atmosphere on the outside. So let's walk through how a simple, everyday task can create this exact danger.
It all kicks off with a really common maintenance job, cleaning out a big industrial vessel with steam. Seems totally harmless, but it's the sequence of events here that really matters.
Okay, so first things first. Hot steam gets pumped into the container. It pushes all the air out, does its cleaning thing on the inside surfaces. At this point, the pressure inside is just a little bit higher than the atmosphere outside. Totally normal. And now, this is the critical part. The job is done, so the operator shuts all the valves. The vessel is now a completely isolated, sealed system, and it's full of hot water vapor. And then, they just leave it to cool down. The steel starts radiating heat out into the air, and the temperature inside slowly starts to drop back to room temperature. So here is the million-dollar question. As that trapped steam goes from hot to cold inside that sealed box, what do you think happens? This is where the physics really gets interesting. All right, now we're going to see how this simple act of cooling has just created an invisible but absolutely overwhelming force. As that steam cools down, it does what steam does. It condenses. It turns back into liquid water. But here's the kicker. That massive volume of steam gas collapses into just a tiny little puddle of water on the bottom of the tank. And since there's almost nothing left to fill that space, the pressure inside the tank just plummets. You've basically just created a near-perfect vacuum. All the while, the pressure on the outside hasn't changed one bit. And this creates a massive, and I mean massive, pressure imbalance. See, the air all around us is constantly pushing down with about 14.7 pounds of force on every single square inch. We don't feel it because the pressure inside our bodies is pushing out just as hard. But that sealed vessel, it just lost all its internal pressure. It now has the full weight of the sky bearing down on it from every single direction.
And this is such a great way to put it. A vacuum doesn't actually suck. The atmosphere pushes. That vessel isn't being pulled inward, it is being violently crushed by the weight of the very air that we're all breathing right now. So how on earth do engineers stop this from happening?
Well, this is where process safety engineering comes into play. You've got industry standards like API 521 that specifically lay out how to protect against these vacuum conditions.
And it really boils down to two main strategies. The first is a simple passive mechanical device, and the second is a more active, instrumented system. So a vacuum relief device, or a vacuum breaker, is pretty much the exact opposite of a pressure relief valve. Instead of letting pressure out when it gets too high, its whole job is to let air in, to stop a vacuum from ever forming.
And it's so elegantly simple. The second the pressure inside drops below the atmospheric pressure outside, that 14.7 psi of air literally pushes the valve open. Air rushes in, the pressure equalizes almost instantly, and the vessel is saved.
The other way to do it is with a repressuring system. Think of this as an active defense. It uses instruments that are constantly monitoring the pressure, and if they detect it starting to drop, they automatically inject a gas, usually nitrogen, to keep the pressure up and prevent a vacuum from ever forming.
Now, this whole steam cleaning thing is a classic textbook example, but the danger of a vacuum collapse can pop up in all sorts of different situations.
For example, you could just be pumping liquid out of a sealed tank. If you don't let air in to replace it, that tank can implode. Or, get this, a sudden cold rainstorm hitting a hot tank can cool it down fast enough to cause condensation and collapse it. Even some chemical reactions can absorb vapor and create a vacuum.
And that's really the main takeaway here. Protecting a complex industrial plant means you have to think way beyond the obvious stuff. Engineers have to plan for explosions, sure, but also for implosions. They have to think about what can go wrong not just during normal operation, but during every single phase of that equipment's life.
And standards like API 521 are what help define the boundaries. They basically tell engineers what they must design for, these single, credible events, while also saying, hey, you can't realistically design for every wild combination of failures happening at once. It's a concept they call double jeopardy.
So, at the end of the day, real safety comes from looking at the whole picture. It's about analyzing every single step, from startup to shutdown to routine maintenance like steam cleaning, to find and fix these hidden dangers before they ever have a chance to become a disaster.
It really makes you wonder, doesn't it? Our world is just full of these invisible forces like atmospheric pressure, and so much of our modern life relies on some really clever engineering that keeps them all safely in check. What other unseen dangers are being quietly managed all around us, every single day?